hear you.
I didn't know if you were in class or not. I didn't see you talking.
I haven't started. It starts at 2:30.
Okay. So why did you become a dean?
Oh, that's just inadvertent.
I know you came down maybe to see me, so I thought I'd stop in.
No, I was just bored out of my mind.
Yeah, early here. Well, your class goes to about 5.
No, 3:30.
3:50.
3:45.
Yeah, I'm gonna be here waiting to see if my little prodigal son comes. He said he's gonna come see me and get help, and then did it, and said, can I move it? And then I said, I can move it to here. And I said, send me a time. Haven't heard from him.
I've got the workshop, Foster Center workshop at 7:30.
Night?
Yeah.
Oh, right during my little review session.
Yeah.
Here comes his question. You know, doesn't he look like he's dragging back in here after a tough day? Is that Mike or not?
Yeah, that's Mike. Yeah.
And he looks like he's whipped. That's what we all look like after we teach.
Should we tell him to put a little spunk in his step?
He's out of it.
Poor guy.
Poor guy. Poor guy. It's so bad.
I got all these students here. What am I going to do?
Talk to him.
Hi, everyone.
I emailed the students and asked them today, do you have a computer? Do you have a computer?
Did they?
Yeah, do you have an internet account? It tells me when they shut down all the kids. I think all the kids say, I don't have this account. So they don't think they're going to shut down yet, but they think it's coming. So you're going to be gold because you're already online 100%.
I already made that mistake. Hi, everyone. Welcome to school today. Does anybody have a funny or a humorous anecdote of college life they'd like to share with us? Does anybody have a funny joke they'd like to tell us?
I got one.
Oh, yeah. Hey, sure. Man of the hour. Let's go. Rock on, dude.
So what do they call a deer with no eye?
Anybody? I don't know.
No idea.
Oh, that was good. That was good. That was good. Thank you. Massive extra credit to you. It gives you everybody thought, right? Did I ever tell you guys a story about I was teaching economics at Fordham one time, and I did an experiment, and I told the kids I needed a volunteer, and of course nobody volunteers, just like you lot, right? Nobody says anything when I say, hey, what's going on? So finally some kid volunteered, and I gave him a king-size Snicker bar, right? So then I asked for a second volunteer, and the whole freaking damn class volunteers, right? Anyway, I get this girl who happened to be failing the class. And I said, instead of a Snickers bar, I wanted her to go to the whiteboard and provide all of the class with some artwork. So she pulled the wrong end of the stick, right? So you know what she drew on the board? A picture of me. All right. Hey, one of you who I don't see. Oh, everybody send me a hello in the chat so I know who's here. So remember the other day, we were talking about, I was going over that portfolio variance idea, and I showed you the R code, yeah, where I had 3 stocks. And some of you complained about me doing this. Well, here's what I did. I wrote it all up. So you see here the PDF of portfolio variance example. I wrote up a story about what I was trying to tell you all. Okay? An example of what I meant to demonstrate. So there are a number of pages that I wrote up here, and I hope that it makes it clearer. These are the stocks that I used in that R code. And then, of course, I went through some of the definitions of what we're doing. And I showed you another matrix. Okay? So that's there for your benefit. I did the very same example in Excel. The 3 stocks, calculated the covariance, the variance, the standard deviation, the riskiness of the portfolio. Okay, so this is in Excel. I posted this to Moodle. As you can see, variance of these columns of returns, covariance, variance of the portfolio. And if you read the notes I put up, you'll see it's really basically an explanation of why we're doing what we're doing. Okay, is that cool? Is that going to be helpful? And let me just do it again. I'll show you. Notice we have here 0.84% variance of this portfolio that I calculate with Excel. Many of you are familiar with Excel. If I looked at the code, and I run this code, the answer is the same, 0.844%. Okay? So you can imagine how relieved I was when I did it in Excel and it worked out to be the same number as I did in R. Pretty good, right? So I hope that that answers some of your questions. Certainly, if you're interested, you can ask me more. Please have a look at it and see if it's something that interests you. Okay? let's pick up where we left off, chapter 2, notes, okay? We did this. We talked about the simple regression model, explains why in terms of variable x, y changes with x. Simple model, yield is equal to beta sub 0 plus beta sub 1 times fertilizer plus some error term. Causal interpretation. So we said that the expected value of u, your error term, is not at all related to your explanatory variables x. That's an assumption that we must hold, okay? In other words, this error term contains anything that's not listed in here that may affect your wage. So we know education affects your wage, but we also know innate intelligence, level of training, age, right? All that crap might be in this U, yeah? So, and then we said the population regression function, we said the expected value of y conditional on x is the expected value of beta sub 0 plus beta sub 1x plus u conditional on x. Well, we could just say beta sub 0 plus beta sub 1x plus the expected value of u conditional on x. Therefore, the average value of the dependent variable is a linear function of our explanatory variable. And we see a linear function, population regression function, so x and y, okay? And then we have this equation. The expected value of y conditional on x is beta sub 0, which is your intercept here, plus beta sub 1 times x. Beta sub 1 is the slope of this equation. So we said, you know, we're going to derive the ordinary least square estimate, okay? I'm going to go through the derivation of this ordinary least squares. I don't expect you to repeat it back to me. I don't, it's not something that you need to know. It's something that I need to teach you, right? So this is just the derivation of how ordinary least squares is calculated. And we're going to take the next sort of 8 or 10 slides and talk about this, okay? And I'm going to do my best to do it through Zoom, but I have trepidation about is it gonna go well, or am I gonna lose you? So we'll give it a try. So y'all know, right? We know the values of all the x's and y's, right? We're just trying to create a relationship between them in regression, yeah? So we derive the ordinary least squares. In order to estimate the regression, we need all this data. X sub 1, Y sub 1, first observation, X sub 2, Y sub 2, blah, 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 right? So we're on slide 9. I want to look also simultaneously at my notes. So this is a slide we're looking at, and these are my notes. So if we were in the classroom, I would draw this on the board, right? X sub 1, Y sub 1, X sub 2. These are the points that we're given, and we're plotting them, and we're going to create a regression line, right? We're going to show that Y is the dependent variable, dependent in some way, shape, or form on X. Well, that's what we want to determine. So slide 9, as good as possible. We're trying to fit a line to our data that is as good as possible. What does that mean, right? So let's look at the components to our regression. We have residuals. So whenever you see a little hat over the letter, that's an estimate, okay? So this is an estimate of the error. That's equal to your actual value of y minus your estimate of y, which is equal to the actual value of y minus beta sub 0 minus beta sub 1 x sub I, estimates of these. The process we want to do is minimize the sum of squared residuals, minimize the sum of u squared, the estimate of u squared. And we'll come back to this. Let's look now at this. So we're plotting a line here through our points, x sub y, x1, y1, x2, y2, et cetera, et cetera. The fit should be as good as possible. So given our regression equation, the average of y minus an estimate of beta sub 0 minus an estimate of beta sub 1 times x equal to 0. In other words, the line fits between all the points so that the difference between any point and the line sums to 0. That's the goal here, you know? So we could say, since this is n to the negative 1, this is the average, right? This is 1 over n. This is the average y. This is the average x. So we could say, by rearranging this, that y bar, or the average of y, is equal to the estimate of beta sub 0 plus the estimate of beta sub 1 times x. Okay? So we can rewrite this equation here as beta sub 0 is equal to y bar minus beta hat sub 1 x bar, right? All I did was rearrange this, which is based on this, which is the sum of the differences, okay? What we're doing is ordinary least squares, the least squares estimate of our error terms. So see where this says here. We're going to go to another page that starts here. This is like in class, this is my little tagline to say, okay, explain how we get this. So if you did this, beta sub 0 is equal to y bar minus beta sub 1 hat times x bar, you could solve for beta sub 1 and get this. Now I want to go to here and show you that. This is in my notes. Again, we're in the classroom and I'm writing this on the board, except that I've written it all on pieces of paper. Here's the paper that says here. So we've got this equation. Beta sub 0 hat is equal to y bar minus beta sub 1 hat x bar. We're going to put beta sub 0 into here, right? We're going to put this part of this equation into this equation, which we were just showing you on the previous slide. We're going to get this. Yeah, we just put this part in for this. Do some algebra, and you wind up with an estimate of beta sub 1. Now notice, beta sub 1 hat is equal to the sum of x sub I minus x bar times y sub I minus y bar. What does that look like? X sub I minus x bar times y sub I minus y bar. Doesn't that look familiar to all you dudes? Did you do a major brain dump over summer? Say, yes, Professor Gallagher, I did a brain dump on May 12th. What is that thing, man? The sum of the product of y sub I minus y bar times x sub I minus x bar. Remember it? Anybody? It's the covariance between x and y. Yeah? How about the sum of x sub I minus x bar squared? Does that ring any bells? That's the variance of x. So look, this beta sub 1 is the covariance between x and y divided by the variance of x. These create for us ordinary least square estimates for beta sub 0 and beta sub 1. Now we need to choose beta sub 0 and beta sub 1 to make the sum of the estimate of error terms squared as small as possible.
I woke up in the middle of the night so thirsty.
I know you were
Okay,
like, is there any
so this is
water
what we're
there?
doing here. We've got
And I
beta sub
just
1.
went back to bed. I'm sorry. I'm so tired.
For a second, you had me. I thought you were gonna get up and give me some water, but you just rolled over.
Hey, Drake. Drake?
Yeah.
We can all hear you.
Oh, sorry.
Okay, so here's where we left off, and this is what I said I would come back to. Notice, we know beta sub 0, we substitute it in, we wind up with this. The estimate of beta sub 1 is the covariance of x and y over the variance of x. Yeah, we have the estimate of beta sub 0, which is y bar minus beta hat sub 1 times x bar. Okay, all we're doing is deriving ordinary least squares. So look, this is a picture of our regression. We have all our data points. We have the y sub 1, that's the actual point, right? Y hat sub 1 is the estimate, yeah? The difference between the actual y sub I and the generated predicted value of y is the residual, u hat, right? This is the equation of our line. Y hat is equal to beta sub 0 plus beta sub 1 x, okay? So if we go to the same slide here, so we know we were given this, right? 1 over n, the sum of x sub I minus beta sub 0 minus beta sub 1 x sub I. So that's our standard regression equation, just rewritten a little differently. We can rewrite it so that y bar is equal to beta hat sub 0 plus beta hat sub 1. And then I left when we got to here, right? And I said this is covariance over variance. So these are ordinary least square estimates of beta sub 0 and beta sub 1. So the predicted value or the fitted value is y hat, which is equal to the regression line, okay? The residuals, therefore, the u hat sub I is a difference between your actual y and your estimated y, yeah? Now, the idea is to make the sum of those squared residuals as small as possible. So we know the sum of u squared is the sum of this. This is a calculus problem. I'm not asking you to do this. I'm not even asking you to remember all of this. I'm just telling you what's going on, okay? Remember it or not. All right. So what does good as possible mean? I think this is the slide we were just looking at. What does good as possible mean? So we've mentioned already a couple of assumptions. The expected value of our error term must be 0, right? If we have the best line, then the sum of all those things are going to be 0. The covariance between x and the error term is equal to the expected value of x times the error term, which is 0. Because we said the error term has to be uncorrelated with any value of x. We cannot have a relationship between the error and the x, okay? So given that the expected value of u, your error term, is equal to 0, then y equal to beta sub 0 plus beta sub 1 x plus u must mean that u is equal to y minus beta sub 0 plus minus beta sub 1 x. We just did some algebra here to get u off by itself, right? So the expected value here, the expected value of y minus beta sub 0 beta sub 1 is 0, and the expected value of xu must be 0. So we can just plug this in. We're saying if the expected u is 0, plug that into here. So the expected value of xu is equal to 0 can become the expected value of x. We set up here, u is equal to this. So plug this in. These provide the estimates of beta sub 0 and beta sub 1 for our sample counterparts. Okay? Now, come back to the slides. Okay, it's really only 4 or 5 slides that show you how to derive this. And like I said, I don't want you to do it. But in my notes here, it's just really from here, this is that extra page I slipped in there. And now we're here, right? So this is the slide that we got to. I've gone through the derivation. I've gone through the derivation of ordinary least squares in regression, okay? Just so you know where it's coming from and what we're talking about. Now, let's continue and we'll talk about more tractable stuff that you could probably relate to easier. Let's try anyway. So here we're regressing salary on the ROE of a company. We would imagine that salary might be related to return of equity on a corporation, right? As it happens, we have this regression. The estimate of salary is equal to 963.91 plus 18.5 times return on equity. In this regression equation, we have the intercept here. This is our value of y, naturally. This is our value of x. This is beta sub 0, or the intercept, and this is beta sub 1. Yeah? And what this equation tells us is the return on equity goes up by 1% here, then salary is predicted to change by 18,501. Okay? Let me see what I wrote on my other slides. my classroom slides. This is taken from data set CEO Sal 1, which hopefully you've all downloaded to your computers by now, right? Measures the change in the estimated salary for a change in return on equity, which is what I just said, right? Return on equity and salary. Let's go back to the real slides here. Damn. Here's our regression line. This is what the picture looks like. The intercept, salary is our Y value, return on equity is our X value. The fitted regression line, depending on the sample. Yeah, that just means depends on the sample that you take. And then the real population line out in the population, we don't know. We'll never know. Yeah. How about wage and education? So wage says that beta sub 0 plus beta sub 1 is equal times the years of education plus some error term, right? The fitted regression is your estimate of wage with an intercept of negative 0.9 plus 0.54 in education. In other words, in the sample, one more year of education was associated with an increase in hourly wage of 54 cents, right? If you go to college one more year, you get 54 cents more an hour. How about this, negative 90? Somebody tell me, what is the interpretation of negative 90? No, not all at once, please. I can't handle it. Chill your bones, guys. One at a time. This feels like one of those games, you know, that you play with little kids when they're driving you out of your mind and you say, hey, let's see who can stay quiet the longest, right? Anybody want to hazard a guess before I call on someone to interpret for me this intercept of negative 0.9 in this regression equation?
Is that the base salary? Base wage, right?
Is that William?
Yeah, that's me.
Yes, it's a salary, but at what point?
0 years of education.
Like the base, like the beginning.
Perfect. Thank you, Drake. Thank you, Will. Does that make any sense? If you've got 0 years of education, what do you got to pay them to work? Negative 0.9? You got to give them like 90 cents for every hour you work. Doesn't have any interpretation, right? So sometimes the intercept, it's as meaningless. Yeah? Thank you, guys. I appreciate your contributing. All right. What do I say on my other slides? Let me just have a look. The population regression line, we did this. We're talking about this. Y is equal to wage, dollars per hour. Wage is $6.75, means $6.75 per hour. Education is years of schooling. This is taken from data set wage 1. If you were to look at that, what does the intercept tell us a person with no education has a predicted hourly wage of minus 90 cents. All right, let's look at the next one. Voting outcomes and campaign expenditures. So we have the percentage of vote for candidate A is some regression, beta sub 0 plus beta sub 1 times the percentage of campaign expenditures for candidate A, plus an error. The fitted regression tells us that the estimated vote for A, percentage of vote for A, is 26.81 plus 0.464 times the share of A. In other words, if candidate A's share of spending increases by one more percentage point, he or she receives 0.46 percentage points more of the total vote. So I want you to be careful with terminology here, because what we're saying is you regress Y on X, yeah? You're always regressing your dependent variable on your independent variable. The independent variable is the variable that you can change, right? Campaign expenditures. And the result, or the dependent variable, is your Y variable, right? Okay, let's look at the more terminology. Properties of ordinary least squares on any sample, fitted values and residuals. So Y hat sub I, is equal to beta hat sub 0 plus beta hat sub 1 xi. These are predicted or fitted values. This is the estimate, yeah, given our real values, which would just be Y. So deviations from the regression line, in other words, residuals, is your U hat sub I, right? I is each independent observation. Y sub I is each actual observation, each value of Y, minus your estimated value of Y, or the fitted value, or the value on the line, your regression line. Algebraic properties. The sum, so we read this as the sum, as I goes from 1 to n, of U hat sub I must be 0. So the deviations from the regression line sum to 0. Let's go back up to look at a regression. All these deviations between the actual and the line sum to 0. That's our assumption. The sum, as I runs from 1 to n, of x sub I times the estimate of U sub I must be 0. The covariance between deviations and x is non-existent. Yeah? The sample averages of y and x will lie right on your line. So the sample average of y and the sample average of x, y bar is equal to beta hat sub 0, blah, blah, blah. Okay. Here's data from, I think this is CEO salary and return on equity. So this would be a data set somewhere in that whole data set that you guys have downloaded to your computers, right? So let's just look. We have a return on equity. We have observation numbers. This is just an excerpt, yeah. The salary, right? So this is Y, is your salary. That's your dependent variable. Salary hat, that's the estimate, yeah, given the return on equity, and the estimate of your error term. So some of these are pretty big. Look at U sub I hat, right, minus is equal to the actual Y minus your fitted value of Y. There's some big differences here. Look at this one. CEO salary, CEO number 12 salary was $527,000 lower than predicted using the information on his firm's return on equity. So this tells me to have such great big differences between actual values and your line tells me there's a very wide variability in CEO salaries, right? I mean, it's like huge, yeah? So let's keep looking at this. Very exciting, right? Let's keep looking at this. Goodness of fit. How well does this explanatory variable explain the dependent variable, right? The explanatory variable in our example we just looked at was what? Return on equity. How well does return on equity explain CEO salary? Yeah, you would think CEOs of companies get paid depending on what return on equity they have in their company. So let's talk about how do we measure the variation in this stuff. I just said, I thought, oh, these points must be really all spread all over the place because one salary was $500,000 off. So total sum of squares. Total sum of squares is the sum of the difference between your actual Y and the average value of Y. Total sum of squares. The explained sum of squares represents variation explained by the regression. So this is the sum of your estimate of Y, Y sub hat, minus the average value of Y squared. The residual sum of squares represents variation that we are unable to explain. This is the sum of your squared error terms. Yeah? So naturally, on my notes, I've written all these things on the board. So in class, if you were in class, you would be furiously writing these things in your notebook. But since you're not in class, I don't know what's happening. Here we go. Here, see, I would be writing all these things on the board, and you would be writing them in your notebook. But now you know that they're here because I've written them for you. So the total sum of squares must always be the explained sum of squares plus the residual sum of squares. In other words, this must always be equal to this plus this. That leads us to this, which you're all familiar with. Total sum of squares is equal to explained sum of squares and residual sum of squares, the R squared measure, right? R squared is the relationship between the explained sum of squares and the total sum of squares. In other words, R squared is how well are we explaining this data, this information, yeah? How well does return on equity explain CEO salary, right? That's what the R squared of that regression should tell us. Measures the fraction of the total variation that is explained by the regression. If we look at your supplemental notes, if you were to divide total sum of squares up here by sum of explained sum of squares and residual sum of squares, you would get this equation 1 minus residual sum of squares over total sum of squares, which is R squared. Yeah, R squared, the ratio of explained variation compared to total, i.e. the fraction of sample variation in Y that is explained by X. Let's go back here. CEO salary, 963 plus 18,501 per return on equity. 209 observations in total. The R squared is 0.013. The regression explains only 1.3 of the total variation in salaries. Does that jive with what I said about these points being all over the place? Yes, of course it does. Yeah, the R squared is horrible, right? What is it? What they say? 1.3% of CEO salary is explained by the return on equity in the firm, right? That's horrible. Let's have a look at the voting outcome one. Oh, voting outcome. Well, this was a percentage of money spent by candidate A and the percentage of vote that candidate A got, right? Well, this regression has an R squared of 0.85. That's 85% of the total variation in election outcomes is explained by how much money they spend. That's pretty significant, right? That tells you that somebody who wants to run for president ought to have a lot of money. Incorporating nonlinearity, semi-logarithmic form. This you could also say is log level. So regression of log wages on years of education. The log of wage. So instead of wage, we take the natural log of wage is equal to beta sub 0 plus beta sub 1 times education. This changes the interpretation to beta sub 1 is change in log of wage, which is change in wage over wage, right? Which converts this to a percentage change over change in education, change in education, change in education. If years in education increase by 1 year. Notice, we're not changing education here. Yeah, we're changing wage from wage to log of wage, which means change in wage over wage, which makes it a percentage change. Yeah, so we said, let's go back here. I want to go back. I want to talk about this. So look at this equation. The estimate of wage, right? This is the same equation. Negative 90, we talked about that, right? You get 90 cents, you pay to go to work, right? And then 0.54. In other words, 1 more year of education was associated with an increase in hourly wage of 54 cents. So here I come. Look at, I'm going to ask you now, does that make sense? So we have a dude that went to school until 7th grade. Yeah? If he had stayed until 8th grade, he would make 50 cents more an hour. Is that reasonable? That's reasonable. Somebody say that's reasonable, Gallagher.
That's reasonable.
Thank you. What about the dude like me that went to school forever, right? And is it reasonable to assume that after I spent 18 years and I got a PhD, that if I did a postdoc for 2 more years, I should get 50 cents more an hour? No, that doesn't make any sense at all. That's what the regression tells us though, right? That's why we're doing what we're doing. That's what's going on right now. Hang out to your seats because it's very exciting. It's right here. Because we converted this to log, that's a percentage change. The wage increases by 8% for every additional year of education. In other words, that's much more realistic, isn't it? So the seventh grader that's decided to stay in school for another year of school, he's going to get 8% of like the $15,000 that he makes every year. Yeah, but the PhD who has done a postdoc who's making, you know, 150,000 a year is going to get 8% more of 150,000. Doesn't that whole idea make much more sense? So this is the motivation for using logarithmics. It changes this to a percentage change. Yeah, very important. So look at log salaries. This is log form. Yeah, instead of the one we had here was log level. This is log, right? So log of salary and a log of sales. This is a percentage. We changed these to percentages by converting them to logs. So your beta sub 1, or the slope, is a change in log salary, is a change in salary over salary. That's a percentage change.
Is the result gonna be the same if it's log or log and non-log?
Well, the interpretation is the same because we were looking at this as dollars. Yeah. So before, when we said we ran that other regression, these are dollars.
Okay, thank you.
Now we're saying they're percentages. You know, so it's no good to say that a CEO makes $200,000 a year if they have sales of $500,000. But it's much more sensible to say the CEO's salary depends on, it will go up by a percentage of the percentage change in sales. That's what this is saying. So you're converting this from actual dollars to percentage change in dollars. Matt, does that help?
Yeah, thank you.
Okay, so same thing here, see? So we have a percent change. Log form postulates a constant elasticity model, where semi-log, where we said it was log level, assumes semi-elasticity. You can relate this to, remember when you studied economics and you studied elasticities, right? And so the elasticity of demand, remember how the curve went, the curve went like this, right? The demand curve wasn't a straight line necessarily, and they tell you in ManQ, oh, it's a straight line, but it doesn't necessarily mean it's a straight line because it's different if you're up at, you know, a small Q and a high price than it is when you have a high Q and a low price. It's because it's elasticities that you're considering. Remember that from economics? That's what we're talking about. Okay, everybody styling still? All right. Expected values and variances of the OLS. The estimated regression coefficients are random variables because they're calculated from a random sample. We are interested in beta sub 1 estimate, so beta hat sub 1, which is your slope. This is the covariance of x and y over the variance of x. This is the slope of that line. Beta sub 0, the intercept, where we just say, hey, this is just algebraically manipulated to say y bar minus beta sub 1 hat times x bar. So the question, what we're interested in is how accurate are our estimates of beta sub 1 and beta sub 0, right? So the data is random, depends on a particular sample that has been drawn. The question is, what estimators will estimate on average how large the variability in repeated samples? The estimate of your beta 0 and beta sub 1 and variance of beta sub 0 and variance of beta sub 1. We want to know, you've got I don't know, you want to know the height of all the 20-year-olds in America, yeah? So you take a sample of St. Bonaventure's 20-year-olds, and you say, well, what is their height? And you get, 5'9". Well, then you go over to, Fredonia, and you take a sample of all their 20-year-olds, and you get 5'10". And then maybe you go to Penn State and you take all their 20-year-olds, and you get, 5'7". Well, which is right? Right? Which is right? The answer depends on the variability of your sample set. And that's what we need to explore. Is this sample set accurate enough to provide us with an accurate measure? Okay? So these are the assumptions of the linear regression model. Assumption 1, beta sub 0 plus beta sub 1x is equal to u. In other words, the relationship between y and x is linear. The data is random, assumption 2. Each data point therefore follows a population equation. Discussion of random sampling for wage and education. All workers at country A, linear relationship between wages or log of wages more likely, and years of education holds. Draw a completely random worker from the population. The wage and years of education drawn are random because no one knows ahead of time which one is drawn. Throw that worker back in and then repeat the random draw. The values drawn for the ith worker. So we have the actual y that we selected, right? We're selecting and we're creating a sample. The implied deviation from the population relationship, that's our error, u here, right? So we have y sub 1, this is y sub 1, u sub 1, for x sub 1. This is x sub j, right? So for all the values of x, we're going to have this experience, yeah? And we have this u sub I, which is our error term, is a difference, right? Between the line and the actual y, okay? Assumption 3, variation in x is necessary. If the standard deviation is x in x were 0, then assumption 3 would fail. So the difference between x and the average value of x must exist. If you had all the same x, well, what would you be achieving, right? If every kid was 5'9" and you wanted to know the average height of all the kids, I mean, well, what would you achieve, you know? So the value of the explanatory variables are not all the same. Otherwise, it would be impossible to study how different variables lead to different variables of the dependent. Zero conditional mean, we've talked extensively about this. The expected value of the error term conditional on x is equal to 0. Value of the explanatory variable contains no information about x. So we have, I think this is the last thing I want to talk about, unbiasedness. The interpretation of unbiasedness through the assumptions of the simple linear regression 1 through 4 is that the expected value of your estimate of beta sub 0 is actually beta sub 0. The expected value of your estimate of beta sub 1 is actually beta sub 1. Okay? My notes, you'll be delighted to see. This is what we're saying. This is the definition of unbiasedness. The expected value of your estimate is the real value out in the population. The expected value of your estimate is the real value out in the population. On average, over many draws, the estimate will equal the true value. Unbiasedness. Variance of the OLS estimators. Let me just look at quite a lot more, actually. Damn. How's everybody doing? Is it too much?
Good.
Say it again, Matt.
It's not terrible.
Not terrible. Have I done too much? There's like eight more slides. You want to stop today? Are you guys going to be able to keep up?
I hope so.
All right. You know what? I'm going to stop today. When we come back, let me just show you on Tuesday. We were going to talk about the variance of the estimators, homoscedasticity and heteroscedasticity. Very important. The variance of these estimators and the sampling variability. Okay, but we'll do that when we come back on Tuesday, right? If anybody has questions, let me know. And I do hope that you will look at the material I posted on that portfolio variance, if nothing other than just because it's interesting. Okay. All right, everybody. Have a good weekend.
All right, thank you.
Thank you so much.
You too.
Have a good weekend.
You too.
Thank you.
You too. Thanks.